Hello everyone, my name is Aritra. So today in this I will present the transport phenomena assignment, the 6th semester chemical engineering department under the Professor Mahesh Verma sir. So in this assignment I will discuss about the heat conduction with a nuclear heat source. So first of all we can see this diagram where there is a spherical structure, and in this spherical structure this is a spherical material of sphere. Outer surface is with aluminum cladding. We can see that the aluminum cladding is outer there, like these are two concentric circles, and the outside is flowing coolants to cool this temperature. So at that sphere the heat is generated, and due to the heat generation the temperature flow will be from inside to that outside portion. Like if we see, heat will be flowing from inside to the outside portion. So heat will be generated in the fusionable material, the temperature will be high, and the temperature will be flowing from the higher temperature to lower. The outer surface temperature will be T0 of that cladding. We can see in the 3D structure, RF is the radius of that fusionable material, and RC is the radius from the center to the cladding outer. So we can see the higher temperature to lowering. So in this we will do with the balance equation, the cell balance equation. Moving to the next slide. So this is that the formula how the heat is generated. Sn equals to Sn0 1 plus B R by Rf whole square, where Sn0 and B are some constant values will be given that, and R is the radius, how the radius and the generation will be varies, and Rf is the radius of the fusionable cell, what we see here, that the Rf. So if we go with that the shell valence equation, so if we observe that the temperature must be varies with temperature is will be function of temperature of R, theta and phi. Why R, theta, phi? We see that this is a spherical system, and in spherical system if we take some differential equation, differential cell, so for the differential cell it varies with R, theta and phi. If some sphere is there, this is that R will be there, and if the R is varying, theta will be from here to here, phi will be 0 to pi, and theta will be 0 to 2 pi. So if we closely observe the system of a spherical differential cell, if we can see that the temperature will be varies from R, because if the heat is generated, as the R will be increases, the temperature is decreasing. So this is a function of R, temperature. According to theta, we can see that this is that the theta like 0 to 2 pi, this will be the symmetry of that. So due to the symmetry there is not a function of temperature theta. And similarly with phi, if we observe that like how this is like 0 to pi, due to the symmetry also this is also cancelled. So because due to this is because of symmetry. So temperature will be a function of R only. If we observe that temperature will be function of R, where R will be, if we take a differential cell, R will varies from R to R plus delta R, where theta varies from 0 to 2 pi, and phi varies from 0 to pi. These are our differential cell, how it varies. And if we move to the spherical coordinate system and this situation, we are taking generally 4 boundary conditions. So these are like at R equals to 0, when that R is equals to 0, the temperature Tf will be there. So Tf is there, so Qf, what will be the heat generated due to that? Like Qf will be finite. at r equals to 0. And if we move to that r equals to rf, like at that position r equals to rf, so when we move r equals to rf, the qf, how much heat is going out from that rf and how much going into that cladding, that will be same at r equals to rf. And r equals to rf also, due to this flux will be like how much flux going out or how much flux going into that cladding, at that same the temperature of the fusionable material and the temperature of that cladding will be same, because that the flux will be equal. And when that r equals to rc, the flux will be equals to 0 qc, because the heat is not generated at the cladding. So if we go move with that, how much energy balance, the heat rate, we are equating the flux, but flux cannot take in that cell balance equation. The reason is the area is varying. So what will we exactly doing? For that flux, we multiply the cross sectional area. Like this is the spherical surface. If we divide a sphere, that's two hemispherical globes are there. So the hemispherical globes, if we consider that, like hemispherical globe will be like there. Sorry for my drawing. If we consider two hemispherical globe like there, the flux will be in this region Q, and the area will be taking the perpendicular area. So this area, what I have marking here, this area will be 4 pi r square. So the flux into area, we are taking the rate. Why are we taking rate? Because the flux will be changed the flux is depending on that area, and the area will be changing for the spherical coordinate system. So heat rate is generated at that r will be qf into 4 pi r square, the cross sectional area, for this differential cell r equals to r plus theta r, what we are taking here. And the rate of that heat equation also at that differential cell r plus delta r, qf equals to 4 pi r plus delta r. And the heat thermal energy is produced by the nuclear fusion will be 4 pi r plus delta r. Like for the thickness of the delta r, how much heat is generated. Moving to that next. So for that cell valence equation, what we know that the rate of energy of that convective transport going into that, and rate of convective transport going out, and the how much molecular transport going in, molecular transport out, how much work done to that molecular transport, and how much system work done by that molecular transport, plus the external forces plus energy generated. So for this system, what we are discussing, we can see the rate of conduction is going in and going out for the differential cell is given, and that how much energy is generated with that. So if we observe that this portion is given and this portion is given, this portion, this at the any no external forces, so these portions are not given, so this becoming 0. So our system will be how much energy going in minus going out due to the convective transport plus the energy production. So if we take that cell balance for the steady state, and by that cell balance, if we move that 4r square system, like if we see there is the 4 pi r square and 4 pi delta r square, r plus delta is very small, if we are taking negligible, so it's becoming 4 pi r square. So if we equating that, and if we take that this 4 pi r square below this, so in minus out, this in minus out, and delta r system will be there, and r square, so cancel the 4 pi and there r square. Why we taking this r square? Because the generation is already a function of r square, so we didn't cancel this. So for flux also and this also we can't cancel this, so we take that, and taking the limit at that both side, limit tends to 0, so it's becoming a differential cell like d upon dr r square qf, and putting the Sn equals to Sn naught 1 plus b square r plus r square. Okay. So for the cladding system, what we are discussing, that there is no heat generation. So due to this cladding system, this will be 0, and this is for the fusionable material for the inside, but the heat is generated. Moving to the next, the integral. Now we integrate this equation. Now we will integrate this equation, and by the for this equations also. So integrating this equation and integrating with this equation. So by integration, what we will do, a constant will be coming and taking the r square below, so Sn naught, and for the fusionable material and cladding, we can find that C1 by r square and C1m by r square. So how can we find that C1 and C2? We discuss some boundary condition initially, like for r equals to 0, Q will be finite. So if we put r equals to 0 here for the fusionable material, we can see this portion will be becoming indefined or not defined. That's not possible because Q will be finite. So if we put r0, that will be undefined portion. So what we can do, at that r equals to 0, due to this can be infinite, so we will take C1 equals to 0 at r equals to 0. Okay, so if we do that, the C1 can't be a finite number because this will becoming 0. So C1 we are taking 0. And we also discussed that r equals to Rf, the flux going out from the fusionable and flux coming into the coolant will be equal. So by this, at that Rf, Qf equals to Qc. So what we discussed, that Cf will be 0 because r 0, the Qf will be finite. So what we can find, the equation of for the cladding, if we put Qf equals to Qf, r equals to Qc, then we can find the cladding. For the cladding, the constant what will be, like Sn naught Rf. From here, putting r equals to Rf, so Rf by 3, B by 5, and Rf square. Okay, so Sn naught, this will be equal, so this one will be C1 square, and the r square coming outside, what we here, the Qc r square, so Rf square will be there. It's fine. So what is cladding, and this is for fusionable material. So put that both, we can find that Qf, what will be the Qf for that, and what will be the Qc for that, flux distribution and the sphere of that spherical cladding and fusionable material. These are the flux equations of that with respect to R. Now what we need to find for the temperature profile. So how can we find the temperature profile, as discussed in class about the Fick's law, 4 years law of heat conduction, my mistake, 4 years law. And with that 4 years law, what we discussed, that QR, the flux, equals to thermal conductivity K and the temperature gradient with respect to R's. For this, we will put for both fusionable material and the cladding material. We have discussed here with that 4 years law, what we have discussed flux. So if we put in this equation the Q value of Qf and the QRC, we will get this equation. Kf, thermal conductivity of the fusionable material, temperature gradient with respect to R or X, you can say, dr, it will be like how much temperature is actually changing with that, with respect to temperature, Sn naught plus the equation what you have get, and C1 is 0. And by that the Kc, thermal conductivity of the cladding, and temperature gradient with respect to dr, like what if we are calculating here, dr, and Sn naught plus Rf square, what we are getting that value. We will again integrate this, taking this K and this K below, Sn by Kf, and with respect to dr we are integrating this. If we integrate this, we find equation of Tf and Tc, and also get some integral constants, Nf plus Nc plus C2 r square by 6 b by Rf square at to the power 4 by 20 plus C2f. Tc will getting Sn naught by Kc 1 plus 3 by b by 5 Rf cube by r plus C2. Here C2, f and C3 are the both integral constant. So we were mitigating this by the boundary condition what we have discussed. So we have discussed at that r equals to Rf, that Tf will be equals to Tc, and r equals to Rc, the Qc will be 0. So R equals to RF, TF equals to TC, and RC equals to TC equals to T0. Okay, these were the boundary condition we are applying due to we want to find this integral constants here. So if we put that values also for that's RC equals to T0, that RC, if we put that, we can take that value from here, like we can find that TC and C2 will be value will be T0 plus SN0 by Kc RF, and R putting that value of RC, and this will be value what we are getting for TC. And if we equate that TF and TC here, we are getting TC will be SN0. This is we are getting from this equation, TC equals to T0, and by this we will find the TC by putting this C2 value, this C2 value from here. So we will get the TC equation, and by that TC we equate the TF and TC, so we will find the C2F. We will here find the C2F, and here the C2C what we find. We put this constant value at the TF and TC, so we will find that TF equation will be what we will find that the TF equation will be SN0 plus RF square 6K fusible material का thermal conductivity 1 minus RF by R square plus 3 by 10B, and the equation of 1 by R. This is coming due to the C2 value, this C2 value, and taking the whole constant with that, we are getting T0 is that ambient temperature outside that sphere. So this is the expressions where the T0 is the ambient temperature, TC is the outer temperature of the cladding, and TF is the temperature at RF. Now if we want to find the maximum temperature, so what we can do, generally differentiate the TF, like maximum temperature of the fusible material. So if we differentiate the TF, we will get this equation, TF by TC SN0 Kc. So if we can see here, like if we took that, the SN0 by Kc will be a term, Kf will be a term, and there is a term R by 3, B by RF square, R cube by L. So this term can't be 0 because these have some positive values. Okay, so this term can't be 0. And if we take common, R common, 1 by 3 plus R square. Hello everyone. So now in this chapter we will discuss about the heat conduction with a nuclear heat source on a cylindrical system. So before we discuss about the circular system or circular coordinate system, now we will discuss when a cylindrical system like some pipe or some cylindrical reactor is there. So suppose this is a cylindrical reactor, yellowish you can say, the yellow line. This is a cylindrical structure where the inside the heat is generated as the same equation, Sn equals to Sn0 1 plus B by B into R by RF whole square. So there is the cylindrical structure, and outer surface, the blue line you can see, this is a cladding, like supporting the, for preventing the losses of heat, and outside there is a coolant for the cooling surface. The coolant has some ambient temperature like TL, and in the inside their maximum temperature is about 1900 degrees Celsius, and there is a charcoal cladding, and their maximum temperature at the surface would be there. So this is the clear cylindrical coordinate system. So cylindrical coordinate system, and this is the graph. We will come to this later. So suppose this is a cylindrical coordinate system, cylinder is given, and this you can say there is a radius, like what we discussed, this is the radius, and the theta, like this circular structure, and the length of that. So with the help, if we see that this is the cylindrical structure, RF is the fuel radius and RC is the cladding radius. So for the differential cell, if we consider for a cylindrical structure, if we suppose we should take a differential cell, so we take a part of the differential cell. Suppose this is the differential cell. So what we can see, this is the radius and the theta and the amount of z we are taking. So if we see for the cylindrical system and differential cell for energy balance, we can see that around the theta there is no flux change actually happening. So by simplification, if this we cut this and made a flat sheet like, so how much is going by this thickness out will be come to the same. So it's circular way, like it's symmetry about the theta. And about that z, if we consider the first portion when it's comes to the ambient surface temperature and the last portion, these are the end effects. So we will neglect this as end effect neglect, so we neglect the z direction and theta direction. So we consider the temperature of the differential cell will be varying in that r direction and r from r0, rf and r cladding. So r for the differential cell, r varies from r plus delta, theta varies from 0 to 2 pi and z varies from 0 to l. There are 4 boundary conditions we considered in that spherical cell. So for the shell valence, in is that the area. So what is the actual area we are taking? So if we see, this is the differential cell. Inside the heat is generated. So heat will be dissipated by the surface, the outer surface of that. By this outer surface, the heat will be generated at all direction of r. So the area of this, like this differential cell, will be 2 pi r perimeter into L for the whole cylindrical, and Q is the flux. So Q 2 pi r L, the surface area of that. Like if we are taking this, so the surface area will be the outer surface area of that. The heat in and for heat out, like for delta r thickness, how much energy going in and going out, and generated will be thickness 2 pi r delta r into L, and SN how much generated, watt per meter, centimeter cube per meter cube, how much. So if we go for the shell valence for the fuel fuel sections, like RF sections, so the in minus out into generated equals to 0 because steady state, and this is due to the conductive, because other molecular transport and other is not present, and work external work done is 0. So we are taking this, by taking this SN this side and multiplying by minus 1 and taking that 2 pi r below there. Why we taking 2 pi r below there? Like see, when the RQ is varying actually with respect to R, so if we don't if we take R outside, that's not actually varying of the R. So we take inside the R with Sn, we cancel 2 pi L delta R, taking that limit, so it's becoming the differential of that and taking integration on both sides. So we can find this QR taking R at the below, so we find that the QF equation. So what we can see, the QF equation is this. QF will be Sn naught plus beta RF plus C1 S naught is the function is given. If we similarly do cell valence for the cladding section, actually cladding is generating no type of generation. So for that cladding actually we can do with the shell valence and find that QC is C2 by R. So the constant we get C1 and C2. So at boundary condition R, we know that QF is finite because some amount of heat is actually generated from there. So if Q is finite, if we put the value of R0, it's actually C1 by R going to undefined term. So to mitigate this, we try to find that C1 is 0. Then we can tell that QF will be finite. Neither this term will be undefined and the whole term will be becoming undefined, and this QF leads to some undefined number. So we to encounter this, we do C1 equals to 0. So find that QF equation Sn naught R 1 plus B RF square R square by 2 For boundary condition at R equals to RF, if we go to this section, at that surface, the flux out of that fluid section is entering at that cladding section. So the QF will be QC at R equals to RF. At applying this boundary condition, we can say that we can find that C2. C2 will be SN naught RF squared 2R 1 plus B by 2. Okay, so we get that QC and QF. We get the flux of that both. So if we know the flux, we read about the formula of Fourier's law. Here is the mistake that this will be Fourier's law. Fourier's law. So Fourier's law, we read about flux equals to thermal conductivity K of that fluid section and the temperature gradient with respect to the direction. Here the temperature is varying on the R direction, so we take dr with respect to. So with Fourier's law, we read about that flux equals to thermal conductivity, negative of thermal conductivity at the temperature gradient. We take both for the fuel section and cladding section. If we put QF at that equation 1, what you see here, QF equals to we see there. So if we put the Fourier's law here, so we can find that the dF by dr, and by that function we can derive about the TF. What will be the TF? TF will be SN naught minus 2kF R square by 2 plus B RF square R to the power 4 by 8 plus C3. We get some constant here, and by applying for that same on the cladding section, we can find for that. See here, if we applied the Fourier's law, we applied that Fourier's law here, and by Sn naught Rf square by 2R 1 plus B by 2 at that QC. By that we encounter that we can find that TC, DTC to TC. We get some constant also because we are integrating, and integral constant is C4. So C4 is here. So we get the C3 and C4 at the constant. We have two more boundary condition here. At the boundary condition we will discuss now. So at that R equals to RC, we can see that here is that surface temperature is not given. If we move with that here, so here the surface temperature of the cladding is not given. So but the ambient temperature of the coolant is also given. So we can see this is from generated here, it's going to RF, this is conduction, and by cladding is also going conduction. But this medium, there is no conduction is happening because there is no particular arrangement of molecule. But there is a coolant whose temperature is given. By this, the heat from this portion will be going through convection process. So convection process, we already know about Newton's law of cooling. QC, the amount of the flux will be HL TC minus TL. TL will be the ambient temperature, and TC will be the surface temperature of that. H will be thermal heat coefficient or temperature coefficient, and QC is that flux. So if we apply the TC, what we have get at the TC, we put that value at the TC, substituting that value at R equals to RC also, and putting the value of QC, what we get at that QC. For that QC we will putting the value of RC. For that we putting the value of RC, and by RC we can get the C4. Actually we are getting C4, putting that equation R equals to RC and substituting the value of TC in the terms of ambient temperature TL, you can observe. So but if we put the value of C4, we also get the TC in the terms of ambient temperature. This is that equation. Same in that R equals to RF, we read about that the temperature of that fuel section and temperature of the cladding will be same. So if we put the value of RF and R equals to RF, putting the value of C3 and the putting values of TC and that RF, we can find that C3 is also coming in terms of ambient temperature and the value, constant value. If we put that TF value, SN0, this TF value where Kc is the heat coefficient, thermal coefficient or thermal coefficient of the cladding material. HF is the thermal coefficient of the fuel material. RC is the radius of that cladding. HL, heat transfer coefficient. So with heat transfer coefficient of cladding also, thermal conductivity of cladding. So we can observe that we can find the TF equation here is given. Now the main portion, how we find the maximum temperature of that. So if we observe that maximum temperature is given from this equation when TT upon dF upon dR. If we observe that, so 2n, if we down this kf, so we observe that Sn0 and kf might have some value, so it can't be 0, because we are why taking 0, because this term, the temperature gradient will be 0, that is the maximum point of that temperature at what radius. So this term R into B by this term will be remaining, like let me mark, like from this portion if equal to 0. So either two options are coming, like R equals to 0 and this substituting term is 0. So the leftover term, if we taking R square one side, if we go the other terms of that outside, it's already coming some negative value if we observe. And R square negative, then R will coming some imaginary number, which is not possible because we can't taking radius and imaginary number. So at that R equals to 0, we can tell we will find the maximum temperature. So the maximum temperature, if we put R equals to 0 at that equation, so this term, this whole term, observe that term, because this is the only term when the radius varies with that. So this term, this will be 0, this will be 0, so this whole term becoming 0. If the marker is not visible, this whole term, what is marking here, this whole term becoming 0, and the Tmax will be this, the leftover term is remaining with. So thank you. This is the portion of the cylindrical covered the question number 3 and 4, and the previous concept, like for the cylindrical system, this concept is covering the question 1 and 2. Thank you for this opportunity, sir.